a pleasure to welcome Silke Rolles. I'm sorry personally that you are not here with us now, but anyway, we will enjoy your talk. So you see the title, and Silke is speaking from München, if I'm not mistaken, right? Are you in München?
Yes. So I'm in Garching in the north of Munich.
Good. So welcome, and please start your talk then. You have 1 hour.
Yes.
You have 60 minutes, including questions.
Yes. I have been watching some of you. So first of all, I would like to thank the organizers for putting together such an inspiring meeting. And I would also thank you to give me the opportunity to speak, although I didn't manage to come. So we are still teaching here. So what I'm going to present is joint work with Margarita and also with Franz Merkel. And I will start recalling the model. So the vertex-reinforced jump process, you have seen it yesterday in Margarita's talk and also in Valentin's talk. But so let's recall. So you have a graph here. You have lambda, the set of vertices, E, the set of edges, and unless in Christoph talks, now it's very important that the edges are not directed. Take your favorite graph for the moment, give weights, WE positive, to all these undirected edges. And then the vertex-reinforced jump process, it's a process in continuous time, let's call it YT. And given the process up to time t, when at time t the process is at I, it's going to jump to a neighboring point, to some j, at rate which is the wij times 1 plus the local time at the destination where you want to jump to. And so you should think of small w correspond to strong reinforcement and large W correspond to weak reinforcement. Why is that? Let's, for the moment, assume, as Margarita did, that all the wij, they are constant. And then when you start the process, it's still sitting at the starting point, and assume all the W are small, constant and small for the moment. So then you have a small rate to jump to a neighboring point. You haven't visited your neighbors, so you have a rate of W to jump to any of them. W is small, so you will sit at the starting point for a long time. But so finally you will jump, and then when you look around, you will have accumulated a very high local time at the point where you came from. So you have a much larger probability to jump there. So much larger rate. So you prefer to go to sites you have visited before, and small w give you a strong reinforcement. So this process was invented by Wendelin around 2000. It's actually connected to the first model that started this area of reinforced random walk, as Jean was pointing out yesterday. So the first model was this edge reinforced random walk. And in fact, one can show, Christoph and Pierre did, that this edge reinforced random walk is a mixture of the discrete time process embedded in this vertex reinforced jump process, if you pick the W's random and suitably distributed. My emphasis here will be on the vertex reinforced jump process. So there has been an extensive literature. You have some experts among you. I will not give a review of the literature. I will just point at a few results which I think are good to know, because I'm going to present you a transient result. So I want you to know a bit about what's known in that direction. So first of all, since you have a non-Markovian process, well, we have to talk about what recurrence transience is, and there is the question of 0-1 laws. And so Christoph, together with Xiaolin Zheng, showed the following. if you have a graph which is infinite and together with your weights W, it's vertex transitive, meaning that it looks the same from every point, then the vertex reinforced jump process, it's either almost surely recurrent, by which I mean that it visits every vertex infinitely often, almost surely, so almost all paths visit all vertices infinitely often, and or if this is not the case, it's almost surely transient, meaning it visits every vertex at most finitely often, almost surely. Good. And then there is this famous dichotomy between recurrence and transience, or at least let's say there are two regimes where we know something about recurrence and transience. A recurrence regime shown by Christophe and Pierre, and also by Omar Angel, Nick Crawford, and Gadi Cosma, is that on any graph of bounded degree, there is a constant W1 such that when you consider the vertex reinforced jump process and all the initial weights are bounded by this constant, then the process is recurrent, or even more, the embedded discrete time process, it's a mixture of positive recurrent Markov chains. And so the argument is completely probabilistically in this paper, which came out simultaneously with the other, more or less, whereas Christophe and Pierre, they rely on work that Margarita was presenting yesterday. And then also Christophe and Pierre, they have for ZD and dimension larger or equal than 3 shown a transient regime, namely there exists a W2 such that when you have constant initial weights, constant weights W larger or equal than W2 for your vertex reinforced jump process, then it's transient. And the last proof, it relies on some substantial work of Margarita with Tom Spencer and Martin Zirnbauer. Good. So you've heard yesterday about the beta field, and so Rémi Poudevigne found very smart coupling of this beta field that allowed him to show some monotonicity in this model, which we and so out of this coupling there come a few consequences which I will use. So here is one of them. Consider now 2 sets of weights on your graph, whatever your graph is. So for HE, you have a WE minus and a WE plus, and the WE plus are always assumed to be larger or equal than the others. And then the probability for the larger, so the probability that your vertex reinforced jump process is recurrent, if you started with the larger weights, it's smaller than if you started with the smaller weights. So if you decrease your weights, you make it more recurrent. Good. And so in particular, when you take ZD, D larger or equal than 3 with constant weights, then there is a unique phase transition between recurrence and transience. In 2 dimensions, I didn't put it here. You have always, for constant W, you have always recurrence, and also in 1 dimension. Good. Any questions so far? Good. Then I come to our result. So jointly with Margarita and Franz, we looked at ZD in any dimension, but now with long-range jumps. So d larger or equal than 1, we take the vertex set ZD, and different from what was done before always, our graph will not be just a locally finite graph, but now we really take the complete graph with this vertex set, meaning you can jump from any point to any other point. And now your weights, wij, are given by a function small w of the distance of I and j. And the w, it's strictly positive, so it's really long-range jumps. You can jump anywhere. And we need some assumptions. So for our result, we need that it's decreasing. We want that the sum of the w of the distance of I when you sum over, so when you take the sum of the weights of the edges incident to 0, that should be finite to avoid or to make sure that your process doesn't jump infinitely often in a finite time interval. And then the regime we are looking at are weights which are not too small, because we want to show a transience result. I said larger weights are weaker reinforcement, so there you expect a transience regime. And so our condition is that this function small w of x is larger or equal than some constant, which is w bar is just a strictly positive arbitrary constant. Then you have a 1 over x to the 2d, and you have a logarithmic correction, a log x to the power alpha, and we need the alpha strictly larger than 1. Good. Under this condition, the expected number of visits to any given vertex is finite. In particular, the vertex-reinforced jump process is transient. I should say that in dimension larger or equal than 3, we can also say the following, namely, it's enough actually to have transients if you have for your wij a lower bound by large nearest neighbor edges. So there is some constant w1 bar positive, such that whenever this constant w bar is larger than it, if you just take wij, whatever they are, they can be, you can have some long range edges, you can do just whatever. Yeah, I mean, you just need to satisfy this lower bound for the nearest neighbor edges, and they have to be large. Then you get already transients. And as I will show in the next slides, I mean, you will use a representation as random walk and random conductances. And in this case, d larger equal than 3 and large w, one can rely on some estimates of Pisatori, Spencer, and Zirnbauer. And then one needs a little argument to really deduce our result. But so in the remainder of the talk, I want to concentrate on this long range result. Good. So how should you think about the condition we have that, so I mean the transient regime here, it's this condition that we have. Well, how should you think of this? And so here, to interpret this, let's look again at another result of Rémy Poudevigne, who showed that when you take the Markovian random walk on a weighted graph G with weights W, and if this is recurrent, then also the vertex-reinforced jump process on this graph with the parameters given by these weights here is recurrent. Good. So we should look at what's known about random walk with long-range jumps, so Markovian random walks. And so there is a result by Caputo, Faccionato, Godelier, and independently there was recently another proof by Johannes Bäumler. And so they consider, the same setup. So they consider ZD, and they have weights Wij. And the random walk, or the Markovian random walk on this weighted graph is recurrent if the Wij are less or equal than some constant times the distance to the power minus 2d when you are in dimension 1 and 2. And it's transient if you have a lower bound, which is the constant W bar times the distance of the vertices to the power s for some s less than 2d. And now one can actually extend the argument of Johannes Bäumler to show that there is also transience if the Wij are bounded by, are lower bounded by 1 over I minus j to the 2d with a logarithmic correction with power alpha, which is larger than 1. So, well, from the first result you see in dimensions 1 and 2, I mean, you need to get something transient. In the Markovian case, you need some correction. And our lower bound that we require then for our function w of x, or no, it's actually for the Wij, it's precisely this one. So one should say Pudovini's result is only shown for locally finite graphs, so you can say, okay, it doesn't apply, but it's believable that one may extend it. Good. So how do you prove results about this vertex-reinforced jump process? Well, you use that it has the same distribution as some random walk in random conductances, as was pointed out in a paper by Christophe and Pierre. And maybe I should put 2015, or I don't know, something earlier. So on any finite graph, finite undirected connected, when you look at the discrete time process xn induced or embedded in the vertex-reinforced jump process, then this discrete time process has the same distribution as a random walk in random conductances, where the conductances are given by Wij, which are the weights we put on our graph, times, something random, so times e to the ui plus uj, and you have a random field attached to the vertices. So at every vertex I, you have a variable ui, which is real valued, and so you put these ui's according to a particular distribution, which you have seen yesterday in several variants in Margarita's and Valentin's talk. And so actually Valentin was giving precisely the joint distribution of these u's. It's so here I put it again, putting some additional variables s. So Margarita was calling these here horospherical coordinates. All this goes so all this goes under the name H22 model for reasons that Margarita explained. And so this is this nonlinear hyperbolic supersymmetric sigma model introduced by Martin Zirnbauer. So for you, all you should know is that we have this representation as a random walk in random conductances. we have this field of UIs, which is some statistical mechanics model, if you like, or if you just come from random walks, you say, okay, that's your environment. And all you should understand, and I think you have understood this by now, is you have an explicit law for this, which is non-trivial. Yeah, I mean, you have here non-trivial dependencies, because in the formula here you have a sum over all spanning trees, and then the sum of these weights over the spanning tree. And in fact, also for edge-reinforced random walk, there has been such a formula, which is this unpublished manuscript by Coppersmith and Diaconis that Jean was hinting at, and actually this paper exists. I even have a copy. But so so this was around in 1986, and just having such a formula, okay, it's nice, but it may not help you. So the reason here that it's helpful is that we by now really have different representations. So we have this explicit law, we have another representation via the beta field, and we also have Zirnbauer's representation, which has Grassmann variables in it, and as such allows the use of supersymmetry. And so that's really the power of this model by now. Good. So what do we do? Well, we want to prove something about the process, the vertex-reinforced jump process on ZD. Sorry, I did something wrong. So you want to prove something about the process on ZD. So you analyze it on finite boxes, finite but large boxes, and you want estimates uniformly in the size of the box, uniformly in the point. So let's take the box here, lambda n is 0 up to 2 to the n minus 1. And we take Weyert boundary conditions. So by this, I mean, whenever your walk would jump out of the box, you jump to a point rho, which is an additional point, and that's the wiring point. And you take the induced weights. So yeah, the weights to the wiring points are just the sum of the weights from a point going out of the box. And then, so by H22 model, for this talk, I just denote the distribution of the UIs you need for this particular graph. When the starting point, so in fact, this, I didn't emphasize this, so the law of these conductances depends on the starting point. Good. So so the point I'm putting here, that's the starting point of the random walk, and so the estimate here I'm presenting is for the environment when the walk starts in the wiring point. Eventually, you are of course interested in the random walk starting at the origin, say, but that's only a well-known Radon-Nikodym derivative, which is e to the minus or plus u0, which you have to add. So that's not a problem. Good. And so we want to bound the environment on this box. And here's the result. So under the assumptions I've stated before, so in particular, you take weights which are given by this function here with this lower bound. We can say something about the mth moment of e to the ui and e to the minus ui. For any m larger or equal than 1, these moments are bounded by a constant, and this constant is independent of the point you are considering inside your box, and also independent of the size of the box you're considering. Since everything is translation invariant, it doesn't matter where I take my box. Yeah, so you can control all moments of e to the ui with respect to this environment. So your ui, they cannot be too large or not too negative. And in fact, for the transients proof, what we need is this estimate for m equal to 5. And the way we do this is we write we want a bound for the expected number of visits to a point. We use that this is geometric and that we can express its mean in terms of effective resistances, where the conductances are, our wij e to the ui plus uj. And this estimate allows us to then compare this mean or this the effective resistance we have for these random conductances with the deterministic conductances, yeah, by just having here a uniform bound. Good, so that's why you want such a bound. In some regime, we have a refined version of this, namely, so we had before this lower bound w of x is larger or equal than an arbitrary constant times 1 over x to the 2d, and then a logarithmic correction with an alpha larger than 1. So now I want alpha larger than 3, and we will need w large. Then we can take an arbitrary kappa positive, and there exists a constant, and there exists a w0 bar positive, such that whenever your constant here, it's larger than the threshold, and you consider now a power which is not larger than constant times w bar, then you can bound the mth moment of cosh ui by 1 plus kappa. So before I had a bound just by some constant. I will say later a bit about how this constant looks like. Here, cosh is always larger or equal than 1. So you cannot get better than so you need to be a bit larger than 1. But here the point is you can actually get constants that get arbitrarily close to 1 under additional assumptions. So for large W, and if you restrict your the moments you want to estimate. Good. So let me just say some words about the strategy of the proof. So I hope I could convince you that to show this transients result, we want to control this random field ui. We want to bound moments of e to the ui or of the cosh. I mean, this doesn't make a difference conceptually. And the way we do this is that we compare the H22 model on lambda n on this box with long-range interactions with an H22 model with hierarchical interactions. And this hierarchical model has some nice symmetries, and using supersymmetry, we can see that the distribution of ui in this hierarchical model agrees then with the distribution in an easier effective H22 model. And then the effective model, we use again some monotonicity. So we can compare it with a purely one-dimensional model with inhomogeneous weights, where the vertices represent length scales. And then one-dimensional models are easy to analyze in this business. Yeah. However, for the refined result, still there seems to be no free lunch. So there we have to go into methods that were used in this work of Disatori Spencer and Zirnbauer. So I want to explain you a bit how we compare with a hierarchical model. So you have seen a hierarchical model and even this picture here in Gordon's talk. So now I want a model on 0, 1 to the nd. So d is my dimension. Here I've drawn d equal to 2. And I want to consider it as the set of leaves of a binary tree. So here, so I don't want to consider a model on the tree. The only reason I've been drawing the tree is to define the hierarchical distance between these points. So I really want such a random field ui living on these points here 0 to 15. And so what's the hierarchical distance of 2 points? It's just in this tree, the distance to the least common ancestor. So these two here have this least common ancestor, so they have hierarchical distance 1. If I take 0 and 2, say, this is the least common ancestor, they have hierarchical distance 2, and so on. And why are you interested in this? Well, we started from ZD, say from Z2 here. And so I have this small box here, and I want to map it bijectively on this. And I think I indicated how I want to map it. So these 4 points go here, and then the next 4 points go there, and so on. And then, when you map it this way, what you get is that you have this inequality. So meaning that the infinity norm of the distance here in the box of the points is less than 2 to the hierarchical distance of the map point divided by the dimension. This thing here on the left-hand side with capital L equal to 2, I think was what Gordon was calling the hierarchical distance. Here, I think we would rather just take the exponent. And so if you look at these 4 points here, they have an infinity norm. If you take any 2 of them, they have an infinity norm of 1. If you look, so there are these points here. So any 2 of them, they have either hierarchical distance 1 or 2. So if you take 1 over the dimension, you have a half, or 2 over the dimension, it's 1. So in any case, you have 2 to the 1. Yeah, so you have 2 larger than 1. So the mapping is in such a way that the points in the blue boxes have distance 1. If you call this here the hierarchical distance in the box, in the lattice, then the one in the green box, they would have hierarchical distance 2 and so on. Good. So formally, what's important is this inequality for us. So that's what we are using. So we have our long-range H22 model with the weights Wij is small w of the distance of I minus j. Then we use this embedding in the set of leaves of the tree. And then we have this inequality. And now we need the assumption that the function small w is decreasing. So then you can make a lower bound for your weights using this inequality. And then here on the right-hand side, you have new weights, which I call W minus, and they just depend on the hierarchical distance. Good. you have smaller weights. You use, again, from the same paper of Remy-Poudevigne, a monotonicity result, which tells you that for any m larger or equal than 1, or actually for any convex function of e to the ui, you have that the expectation is the expectation with respect to w is smaller or equal than the expectation with respect to the smaller weights. And we apply this for the moments e to the minus or plus MUI, which is what we are interested in. So the quantity we are interested in, it's enough to bound them in the model with these hierarchical weights. Now you can say, okay, what have I gained? I still have a long-range model. Well, there is more symmetry in this hierarchical model. And so here's a result we then prove for hierarchical models, which is then enough to deduce the bound we want. So consider the H22 model on the complete graph, now with vertex set 0, 1 to the n and a wiring point. So now I took d equal to 1 because I mean that's an easy translation to do this for general d. And your weights, wij, I now put an h for hierarchical, are given by a function small h hierarchical of the hierarchical distance. And you connect every point with the wiring point with the same weight. And you need some conditions for this function small w of L, and you need again a lower bound, which is constant times 2 to the minus 2L, L to the alpha. And you also need something that the weights to the wiring point are not too small. And then you can show that the expectation in this hierarchical model of e to the minus or plus MUI, they are uniformly bounded, uniformly in the box, and uniformly in the point. Good. So let's see how much I can tell you about this hierarchical model. So what you then do, so here's again such a tree, and we said we have a model which is just on the complete graph here on these vertices. Now we extend this hierarchical model from this set of leaves to any subset of the tree. And for doing this, we need some notation. So L of I is the distance from the leaf. So these points here are at distance 1, at level 1, these at level 2, and so on. I minimum j denotes the least common ancestor of I and j, and bi is the set of leaves above I. So this, okay, so here I've drawn it. The points in B0 are the one here in this box. And then I have to give weights for any pair of vertices ij. I say the weight in this hierarchical model is 2 to the level of I plus level of j times the weight at the level of the least common ancestor. And if you have two leaves, then they are at level 0, so there is no prefactor. And the level of the least common ancestor is then just the hierarchical distance. So that this actually extends the weights we had before now to an arbitrary subset. And now I need the notion of what we call anti-chains. So if you have I and j in your tree, you write I lesser equal than j if I is below or at j. So I2 would be less or equal than this one. And we call a set A in the so a subset of the vertices of the tree an anti-chain if I is not less or equal than j for any ij. So the points here, they form an anti-chain because none is above the other, and I call a maximal anti-chain if I cannot extend it further. So this one here could still be extended by taking this point, and then I would have a maximal anti-chain. And so this is important because we have the following result here, and this is using the particular form of these hierarchical weights and the particular form of the interaction we have, which allows us to say something very nice using supersymmetry. So take lambda n equal to 0, 1 to the n together with the wiring point, and let A be a maximal anti-chain. So you can think of these 6 dots here plus an additional point here. And then the statement is the following: let B be the set of leaves of this anti-chain. And then, well, let's only maybe look at the UJs. So you can also make a statement about the S, but let's just think about the U field. If you look at the U field in this H22 model on lambda n, and you just look at the leaves you have, then that agrees with the distribution of the U field at these same points when you just take the hierarchical model now restricted to this A. Yeah, and in particular, that's true if you have one leaf here. So maybe I indicated here, if you are interested in the distribution of the UI1 in the hierarchical model with this vertex set, then you can equally well look at the distribution, at the marginal distribution of UI1 when you take just the hierarchical model on these 6 points here together with this one. And I mean, I guess it's clear what the advantage is. You have much less points, and you have kind of, so instead of having just all these points interact with each other, you have just some effective interaction between these two vertices. And let me say we can do more. So our result actually gives that whenever you have a point J in the anti-chain, then in the anti-chain model, the e to the uj, it has the same distribution as in the original model, this block spin variable, so this average. Good. How do we use this? So we want to estimate this expectation. Now, by symmetry of the model, the expectation doesn't depend on the point. And so by what we have seen, it has the same distribution as when I take this cosh, let's say cosh u0 or e to the minus plus m u0 in this model for the anti-chain. And here for this particular, I have once written down what you would get for the interactions here. And so you see, you are putting a lot of vertices together, so you will get large weights here in terms of large prefactors. Here I've put it, so let me get a bit, okay. No, I'm even too fast, I'm seeing. Okay, so what you do, okay. So what do we have? So we have this anti-chain here so we have this effective model where we have much less vertices, Of course, here I've just drawn it for a few of them, but I guess it's clear how to extend it to the right. And so in general, you have, say, something like endpoints in your anti-chain. So you should imagine the graph I've drawn. And so then what you have the hierarchical weights, yeah, which we just defined above, and so they turn out to be so the weight between IL minus 1 and IL turns out to be the WH of L and then times 2 to the 2L. And we made some assumptions for the result on the hierarchical model, which were that this here is larger or equal than 2 to the minus 2L times L to the alpha. And so this was chosen in such a way that you get, for this weight here, a lower bound of L to the alpha. And the weight to the wiring point, the weight to the wiring point had a strange looking lower bound, but this was made in such a way that you can think of the wiring point as just being an additional point at the end of your chain, and so that you get the same lower bound. So the hierarchical model can be reduced to this effective model, this model where the vertices form this anti-chain. And there, again, as I pointed out, it's again a model on the complete graph. Above, I've only written what certain weights are. And in fact, you can use again Pudevinius monotonicity to show that you get an upper bound when you just keep these nearest neighbor interactions. Yeah, so when you just consider this here as a 1D chain, then now of course it's inhomogeneous in space. So between any two vertices you have different weights. But then you have a one-dimensional model. And okay, one-dimensional model is easy to analyze. So the first bound I showed you was with an arbitrary constant. So what do? You write your UI with a telescopic sum. In fact, at the wiring point, I didn't say that u rho you put equal to 0. So that's easy. In one dimension for the H22 model, it's known that the increments are independent. So you get a product and you have the precise distribution. And then it's not hard to get precisely an upper bound, which is given by the exponential of 2m plus 1 squared over our constant w bar times some L to the minus alpha. And then you see why we need alpha larger than 1 to make this convergent. And you also see when you are interested, and so that's finite for arbitrary m, so that gives us this bound. When you have w bar large, and you go with m just up to square root of w bar, then you can also get this constant here close to 1. If you want with the m to go even beyond up to scale w bar, then this estimate is not good enough. So if then, then you are in this regime of what I call the refined bound. And so if you want the cosh ui to the m less than 1 plus kappa for m, which go up to scale constant w bar, then you have to work harder, and it seems to us that then you need to use the supersymmetry and methods in the spirit of what Margarita did with Tom Spencer and Martin Zirnbauer. So Yeah, what I presented you was a result about the vertex-reinforced jump process about with long-range jumps. So I hope I convinced you that this model is actually by now quite interesting because we have a huge toolbox, yeah, this allows us to prove things I think we didn't even dream about a few years ago. So I thank you for your attention.
Thank you very much, Silke. And you have time for some questions if there are any in the audience. Yes, Christoph?
Actually, there's something. Could you come back to the statement about the transient regime? So.
Yes.
So. So there's no phase transition in the W bar. No, that's.
No, this is so okay.
So you cannot have. In this regime, it's true. You have delocalization for all W bar. No. Or...
Yes, for all W bar. So at first, actually, I think you heard the talk of me in Oberwolfach, where I still, and also on arXiv, we still have the old version where we needed for the proof W bar large. But in fact, this is true for any W bar.
And do you think there could be a scale in which you have a phase transition on the W bar, such that if W bar is small enough, then you have localization, or in terms of the constant in front of the weight?
I don't have, I didn't think about it, but that so far I don't see any evidence for anything like this.
Okay.
Any other question, comment?
I mean, in the high dimension, of course, when you have this lower bound, it's clear you need the W bar large.
Yes.
Yeah, I mean, and they are, of course, if you have them small, if they are less or equal than small nearest neighbor weights, you know you have a transition. So.
Yeah. Yes, there is one more here.
Do you know anything about the recurrence of this then in the other regime, like something which is not with this scaling, like something less than this?
Well, I mean, I would. Well, I mean, if I so I didn't try to prove it, but then I would first try to see whether one can do anything with Put-Linear, because I mean you have recurrence for the Markovian random walk in this regime. So I would, I think, first see whether this extends to whether this result extends to long range, and then you would have it.
But then I guess there's probably also a regime where the random walk is transient, but the VRJP should still be recurrent.
Can you say that again?
As in, so if this is saying that if the Markov chain is recurrent, then the VRJP is also recurrent. But if the random walk is transient, then
if the random walk is transient, you don't know this this without any further information. So what you know is if the random walk on this weighted graph is transient, and you have bounds as we have for the e to the ui, so these uniform bounds, then for m large enough, so m larger or equal than 5, then you can get transients. But without that, I don't know. And proving these bounds, that's the hard part of the story.
So yes, one more here.
I'm just curious. I mean, it's not very important. Why did you use logarithm base 2, not as natural logarithm?
Because then the formulas came out nicely. And why is that here? Because because you are making this mapping on the binary tree.
Okay. Thank you.
So that's the two.
And I think that was Is there any more question to be asked? No. So let's thank again Silke